I'll just go over the equations on the equation sheet for chapter 28. So the first equation there is the Biot-Savart law. And I've done a YouTube video of how to use this equation to find the magnetic field due to a little element of current. Now I use this DL, I use DS usually, but it doesn't matter. This is the length of current segment. It points in the direction of the current. Okay, so something to be aware of. You've got a mastering physics problem where you have to find the magnetic field due to a little piece of wire up here off. Remember, you have to be a perpendicular distance from a wire in order to have a magnetic field, and the magnetic field lines are circles. But notice that the formula that I derive uses slightly different angles. Okay, so DS points along the wire, R hat points, we want B up here. And so that's R hat. And so I use this angle, theta 1, and then R hat on the other end of the wire points there, and I use this angle theta 2. And the formula has a cos theta 1 minus cos theta 2 in it for the magnetic field. But let's just have a look at how that works. I'm going to define a few more angles here. Let's call this one up here theta 3, this one up here theta 4, and this one down here theta 5. Okay, so the first thing to note is that the cos of theta 2 is the negative of the cos of theta 5. Those two angles add to 90, or sorry, 180. And the cos of theta 5 is the same as the sine of theta 4, because there's a 90-degree triangle. And the cos of theta 1 is equal to the sine of theta 3. And so you can see that this cos theta 1 minus cos theta 2 in my formula can also be written as sine theta 3 minus negative sine theta 4, or sine theta 3 plus sine theta 4. So beware, in mastering physics, the question that you have, it wants you to do this. The answer is expecting the sum of the sines. Now, if it's a perfectly symmetric situation, whoops, that doesn't look very symmetric, but if these two lengths are equal to each other, if these two angles are equal, like if theta 3 equals theta 4, then you just have 2 times whatever this, basically you just have 2 times, let's say these are equal, 2 times sine theta 3. Okay, and that's what mastering physics is expecting. Okay, that's the Biot-Savart law. If you go to infinity, I think I might have done that in the video, but this next formula B for a straight wire, and there's a little infinity sign here, mu naught I over 2 pi r. So if the wire is infinitely long and you have to move a distance r from it, and you get these circles, there's a pi in the formula. Okay, so that's when the current is straight and the magnetic field lines are circles. But if you do a loop, then you flip this. There is no pi. So now the current is a circle. And the magnetic field is a straight line. And there's no, so this is B loop. Okay, and this is B infinite wire. And this one has no pi, the loop. Okay, so be careful of those two. The next formula for the force between two wires, force per unit length. So this has to do with if you have two currents, I1 and I2, and they're separated by a distance R. The force per unit length on them depends on their sum, their product, and then the distance between them. If they're going in the same direction, let's see, do they attract or repel? So I1 creates a magnetic field that's into the page down here. That would be B1. So put your thumb in the direction of I1, and B1 would be into the page. Now do Bill, I cross B. So I2 to the right, turn it in to the page, and you get a force up. These guys attract. So the force between currents going in the same direction is attractive. If they're going in opposite directions, they repel. Okay, so the next one is the loop. I've given you that one. A solenoid creates a nice strong magnetic field. So a solenoid is simply loops of wire carrying a current. And the field, now you'd put your fingers in the direction of this, the current, and your thumb is the magnetic field right through the center of this solenoid. B would be like that. And the formula for the solenoid is mu naught Ni over L. So L is the distance that those wires turn on that, whatever's supporting them. N's the number of turns. So clearly, if you put lots of tight turns of wire, so N over L is big, you get a strong field in the center. Sometimes they define little n as N over L, which is the number of turns per meter. They'll give you that number. The toroid, you don't do any problems with the toroid. And then the next thing is Ampere's law. And I've done a video about Ampere's law. It's similar to Gauss's law for electric fields. It means if you do really symmetric situations, you can have very simple solutions. And for us, Ampere's law is just going to look like this. We're not going to have displacement currents to changing electric fields. We're just going to have currents. Okay, so I've done a video of this. Just like with Gauss's law, you really almost never have to do this. This is just B times the Amperian loop, which is 2 pi r. And that's going to be mu naught I in. And so the working form of Ampere's law, similar to the working form of Gauss's law, is mu naught I in over 2 pi r. Okay, so that's really what we're going to be using. And we only do situations where we have straight pieces of wire. You go inside the wire, you go outside the wire, uniform charge density, non-uniform charge density. And I've done videos of all of those. Okay.